Hello everyone and welcome to Lab 3, which revolves around gravitation based on circular motion. Now today we'll cover the following topics in sequential order, starting with physics principles and the initial conditions surrounding the experiment, moving on to part 1 of the experiment, which is simply just calculating the mass of a black hole given a simulation, and then part 2 is called Don't Crash, more on that later, which is followed by the analysis, summary, and other overarching questions to go along with the lab. Now, the initial conditions. So to start, let's go over our setup. We'll be focusing on a black hole and the objects that interact with it in a given region of space. Now, the initial velocities for all parts of this experiment, as well as the mass that we deducted, are displayed here and will be discussed in detail later on. Now, the few fundamental principles that govern our experiment include the following. So, on the left we have some equations that are relative to the momentum principle, and in turn Newton's second law, as we've seen in past experiments. We have the loose definition that F net is equal to the derivative of momentum with respect to time, and then in this lab we've separated the components. So we have a new concept, is the decomposition of forces into its parallel and perpendicular components, and this is tied to centripetal acceleration. And then on the right we have gravitational force, which is defined as F grav is equal to gm1 m2 over r squared, and we have similar extractions relating to that base equation. Moving right along, we have part 1, in which we calculate the mass of the black hole. So after plugging in my email to assign a random seed generator, we put in some constants, as seen in the first line of code, and then establish our first if statement, as seen in the second. Now, going down sequentially in the code on the right, we first convert velocity into momentum because it's a necessary step in order to calculate the net force. Now, the change in momentum, or delta P over delta T, gives us the net force acting on an object, and from this net force we then find the parallel and perpendicular components. And by rearranging the gravitational force equation and using our calculated net forces, we iteratively calculate the black hole's mass at each step of the orbit, and then I put these values into a spreadsheet in Excel and averaged them, resulting in a calculated black hole mass of approximately 8.4 times 10 to the 33 kilograms. And then moving right along, we have part 2, Don't Crash, and for part 2 we use the calculated mass of the black hole in part 1 to simulate orbital dynamics. And the provided initial conditions are used for coding the simulations. We begin by finding the change in position of objects. We then calculate the direction vector, r hat, by dividing the change in position by its magnitude. Using the gravitational force equation, we compute the forces between the black hole and the planet, and the ship and the planet. And the forces on the planet are summed to get the net force, and then we subsequently perform similar calculations for the forces on the ship. These net forces are then used to update both velocity and position in each simulation step, resulting in a visual simulation of the orbits. And in the simulation you can see the orbit of the planet in blue and the ship in purple. And then just to preface the summary, there's no real source of error, no tangible source of error, since this experiment was executed in a coding setting. And then to answer the discussion question, while net force and change in momentum, the net force and its parallel and perpendicular components differ from the change in momentum over time. And while F net and delta P delta T are equivalent in value, they are not the same in terms of their formal definitions. Meaning the perpendicular component of the net force is simply F net minus its parallel component, and the change in momentum does not have a perpendicular value as described by its equation. And then conclusively, to answer the what if question, I use trial by error to determine the velocities above that'll keep the spaceship in a suitable orbit around the black hole. Thank you for watching. I hope you enjoyed and have a great rest of your day.